welcome to the deep dive. It's so great to have you sitting right here with us today.
Yeah, glad you could join us.
If you are joining us to catch up on where the frontier of artificial intelligence is actually moving, you're in the perfect place. Today, we are drawing our source material from a truly excellent resource called Rooted Layers.
Right, it's AI insights grounded on research.
Exactly.
Yeah.
And throughout our conversation today, you'll hear us refer to it naturally as just the post.
It's a fantastic piece of writing. I mean, the approach they take is exactly what the industry needs right now.
Completely agree. And that kind of dictates the vibe we want to set for this deep dive. We're going to treat this session like two researchers just thinking out loud in the lab. We want to strip away all the marketing hype, all those viral demo videos on social media.
Oh, yeah, the highly edited ones.
Right, and all the noise that usually surrounds AI products. Instead, we're focusing entirely on the research grounding. We want to be curious, calm, and above all, insight-driven.
Exactly, because the goal here isn't to be dazzled by what an AI appears to do in a tightly edited 2-minute promo video. We aren't doing product reviews today.
Right.
The goal is to understand the foundational architecture. What is actually happening under the hood when a system attempts to do real work?
Yeah.
Because when we look at the landscape of AI right now, there is this massive, often misunderstood gap between a system that merely talks about doing a task and a system that can actually execute that task reliably in the real world.
Which brings us to the mission for this deep dive.
Yeah.
We are going to unpack Chapter 8 of the post, which is titled Action Systems and Tool Use.
Okay,
let's unpack this. The core thesis of this chapter is absolutely critical if you want to understand where AI is heading over the next 5 years.
It really is.
The authors argue very firmly that reasoning alone does not make an AI system an agent. Let me repeat that because it's foundational. Reasoning is not agency.
Right.
Being smart or being able to generate a highly articulate, perfectly grammatically correct paragraph of text is not enough. What makes a system an agent is action.
Yes.
It's the ability to reach out into a digital environment, manipulate it, and actually do something.
That's the threshold we are currently crossing as an industry. And for the builders, the developers, or even the strategists trying to implement this stuff, the post poses 3 fundamental design questions. These questions transition us from theoretical intelligence to practical utility.
What are they?
First, what surface should the agent act on? Meaning, where is it actually doing the work?
Right.
Second, how should those actions be represented to the machine? And third, how are action selection, execution, and observation wired back into the reasoning process?
That's a lot to consider.
It is, but these 3 questions are the entire ballgame. They are what separate impressive chatbots from reliable, inspectable systems that you could actually trust to run a critical business process. A useful way to think about this is the transition from an assistant that merely describes work to a digital system that actually performs work in software.
Describing work versus performing work. I want to linger on that for a second because it's such a crucial distinction for you, the listener, to keep in mind. If I ask a standard conversational AI to write me a Python script to, say, rename a batch of thousands of financial files,
Sure.
it can output the code, it can describe exactly how to do it brilliantly, but it hasn't actually renamed a single file.
Exactly.
For it to cross the line into being an agent, it needs to be able to access my secure file system, execute that code, verify the names changed, and report back. And that brings us right into the first major architectural insight from the post, which is something they call the action representation ladder.
It's a brilliant mental model. The action representation ladder basically gives us a hierarchy of how an AI can interact with the digital world. Let's start at the very bottom of the ladder, the weakest rung. Down there, you have plain text.
Just normal words.
Right. Plain text is exactly what it sounds like. The AI generates a string of natural language meant for a human to read. The post points out that this is the weakest form of action representation because it is incredibly hard to replay mechanically and almost impossible to verify systematically. You are basically crossing your fingers and hoping the text contains the right instructions or the right summary, but there's no structural guarantee that another piece of software can parse it.
Let me play devil's advocate for a second, though.
Yeah.
We use plain text for everything. We write emails. We write reports. Why is it so terrible for an AI?
Because of ambiguity. Human language is inherently messy.
True.
If an AI outputs a paragraph saying, I have successfully updated the customer database, and also I noticed 3 errors that I corrected, a human understands that. We get the context. But if you are building an automated pipeline, how does your system verify that?
It can't, really.
Right. Does it run a natural language processing model just to read the output of the first model to guess if the database updated?
It's fragile. There's no standard format. If the AI decides to say database modified instead of database updated, your whole parsing script might break.
Ah, I see. So it's about the machine's ability to verify its own work. If it's just spewing words, there's no proof. It's like an employee telling you they filed the paperwork, but they just yelled it across the room instead of handing you the stamped receipt.
That's a perfect way to put it.
So what's the next rung up the ladder?
The next rung up is code. Now we're getting somewhere concrete. Code is a much stronger representation because it is intrinsically executable.
Right.
You can run a Python script, you can run a bash command, you can test it against a compiler, and crucially, you can see if it throws an error. It either works or it doesn't.
It's binary.
Exactly. But the absolute top of the ladder, the strongest rung, according to the Post, is typed tool invocations in actual environments. Typed tool invocations. Let's define that for anyone who might not be a software engineer. What does that actually look like in practice?
It means the AI is using specific, strictly defined functions or application programming interfaces, APIs,
Okay.
with rigid input and output formats. We call them schemas. Think of it like a highly structured form at the DMV. You can't just write a paragraph about who you are.
Right, they'd reject it immediately.
You have to put your first name in box 1, your last name in box 2, and your date of birth in box 3. A typed tool invocation forces the AI to output its intention in that exact rigid format, like function updated database, customer id 12345, new status active.
That makes total sense. You want the system operating in a space where strict rules apply.
Precisely. If we connect this to the bigger picture, the practical default for anyone designing an agent must always be to move upward on this ladder whenever the environment allows it. You want to get as far away from plain text and as close to typed, inspectable, machine-readable tool calls as possible.
Where failure is obvious and machine-readable, rather than hidden in a paragraph of smooth-sounding text.
Yes.
But the Post also cautions us against a major misconception in the industry right now, which is treating tool use as just one giant monolithic capability. You see this in headlines all the time, right? New Model X can now use tools, as if it's just a single checkbox you tick on a feature list.
Oh, it's far from it. Treating tool use as a monolith is a primary recipe for building fragile systems that fail the moment they leave the testing lab. The research clearly shows that tool use isn't one thing. It is a sequence of highly complex cognitive and mechanical steps.
Okay.
The Post breaks down tool use into 5 distinct subproblems that have to be solved sequentially. If you fail at any one of them, the entire action fails.
Okay, let's walk through these 5 subproblems. Let's imagine I've asked an AI agent to book a flight for me to Chicago for next Tuesday. What is the very first hurdle?
First, there is tool need detection. Does the system even realize it needs to use a tool to answer your prompt? Or is it going to try and hallucinate an answer based on its static training data? It has to recognize, wait, I don't know the live flight schedules. I need external data.
Which sounds obvious to us, but for a model trained to predict the next word, pausing to say, I don't know, let me check, is actually a massive leap.
It really is.
Okay, so it realizes it needs help. What's next?
Second is tool selection. Imagine this agent has a catalog of hundreds of tools. It has a weather API, a calculator, a calendar, a restaurant booker, and an airline API. It has to accurately select the exact right tool for this specific moment, in this case, the airline API.
Makes sense.
Third is argument filling, and this is where things get incredibly dicey.
Argument filling. Let's break that jargon down. An argument in computer science isn't a disagreement. It's the specific piece of data you feed into a tool, right?
Exactly. It's the parameters. Now that the AI has selected the airline API, can it correctly format the specific data required to use it? If the API requires the date in a strict year-month-day format, and the AI provides day-month-year, the API will reject it. If it requires a 3-letter airport code, like ORD for Chicago O'Hare, but the AI just types the word Chicago, the whole action fails.
So precision is absolutely everything there. It's not enough to be directionally correct. You have to be syntactically perfect.
Yes. And once you have the perfectly formatted arguments, the fourth subproblem is safe execution.
Go.
This means actually running the tool in a way that doesn't compromise the system, checking for authorization, making sure the network call goes through, handling any timeouts if the airline server is down.
And then, assuming the server responds with a list of flights, we hit the final step.
The fifth subproblem is the integration of results back into reasoning. The tool returns data. maybe a massive list of available flights, prices, and layovers. The AI has to take that raw output, understand what it means in the context of your original request, and decide what the next step is.
Does it book the cheapest one?
Yeah.
Does it ask you for your preference?
Exactly. This fits a broader pattern we're seeing across all reliable AI engineering. Decomposing complex, vague tasks into bounded, measurable steps. You can't just throw a prompt at a model and hope it figures out how to use a tool. You have to engineer the architecture to robustly support every single one of those 5 subproblems independently.
I love that breakdown. It's like deconstructing the act of driving a car.
Yeah.
You don't just drive. You have to detect the need to brake, select the brake pedal instead of the gas,
Right.
apply the correct amount of pressure, which is the argument filling,
Yes.
safely execute the stop without skidding,
Yeah.
and then observe the road to integrate that new reality back into your decision of when to accelerate again. It's a continuous multi-step loop.
That's a great analogy.
And to really understand how the research community got to this multi-step loop, the post dives into some of the foundational literature that paved the way. It starts by looking at a seminal paper called ToolFormer.
Right. ToolFormer is a massive conceptual bridge in the history of this field. To understand why it matters, you have to look at how things were done before it.
How was it done before?
Well, before ToolFormer, most language models were entirely self-contained boxes. If you ask them a math question, they try to do the math using language prediction, which they are notoriously bad at.
Yeah, they just hallucinate numbers.
Exactly. If developers wanted them to use a tool, they essentially had to build a clunky, hard-coded script on the outside that intercepted the user's prompt, checked if it looked like a math question, ran a calculator, and then fed the answer back to the model. It was a bolt-on solution.
A Band-Aid over the model's limitations. So what did the researchers behind ToolFormer do differently?
They proved that a language model could actually teach itself to use external tools. They did this through a fascinating self-supervised methodology. They took a language model and let it insert special tags into its text generation, like bracket calculator or bracket calendar.
Oh, interesting.
Then they let it generate thousands of texts, pausing whenever it generated a tag to actually call that API and insert the result.
Almost like letting a student take a practice test with an open book and seeing which times looking at the book actually helped them get the right answer.
Exactly. The researchers then measured if the final output of the text was more accurate with the API call than without it. If the tool call improved the prediction, they kept that example. If it didn't, they discarded it.
Clever.
Then they fine-tuned the model on the successful examples. What emerged was a model that naturally, fluidly decided to reach out to tools in the middle of generating a sentence. It showed that tool invocation isn't just a neat trick you bolt onto the outside. It can be an inherent operating pattern. It framed tool use as a behavior-shaping problem.
Meaning the model learns that reaching out for a tool is a natural part of its own thinking process. Just like you or I don't try to calculate 4,598 divided by 73 in our heads and fail. Our behavior is shaped to instantly reach for our phone's calculator. It becomes second nature.
Exactly. It proved that models can be taught when to use a tool. But as we discussed with the 5 subproblems, knowing when is only the first step. You also have to know how. And from there, the post introduces another pivotal paper called Gorilla.
Right, because ToolFormer used a handful of very simple tools: a calculator, a calendar, a translation system. But the real world of software is infinitely more complex. If ToolFormer shaped the behavior, what did the Gorilla research bring to the table?
Gorilla tackled the daunting reality of massive API catalogs. In enterprise software, you don't have 5 tools. You have 5,000.
Yeah.
You have AWS APIs, Google Cloud APIs, internal microservices. Gorilla framed tool used specifically as an API understanding and argument construction problem. The researchers noticed that general language models were terrible at writing API calls. They would constantly hallucinate parameters that didn't exist or use outdated versions of the documentation.
Which goes back to that strict schema we talked about. If the AI calls the API with the wrong parameter name, the whole thing crashes. So how did Gorilla fix this?
The Gorilla methodology involved fine-tuning a model specifically on a massive data set of machine learning APIs. They essentially trained it to act like an expert systems integrator. What's fascinating here is that when you look at why agents fail in production today, it usually isn't because the underlying model lacks broad general intelligence. It can write a beautiful sonnet.
Right.
It fails because it selects the wrong tool out of a database, or it completely messes up the parameters it feeds into that tool.
So Gorilla was about teaching the model the rigorous syntax of the digital world. It's the difference between knowing you need to speak French to order at a Parisian cafe and actually knowing the precise vocabulary and grammar to get the meal you want.
Exactly. Gorilla focused on how to make models highly accurate at retrieving the right tool specification from a massive catalog, which we call retrieval augmented generation, and then generating the exact right JSON schema to make the API call work flawlessly. It moved the needle on that critical argument filling subproblem.
This is a great progression. ToolFormer gets the AI to realize it needs tools. Gorilla gets the AI to write the complex syntax to use those tools correctly. But let's escalate the complexity even more.
Let's do it.
What happens in situations where a task is so large, so multifaceted, that it requires multiple different types of tools or even different types of AI models working together? If I want an AI to read a financial report, generate a predictive chart, and then email a summary to my team, that's not one API call. The post brings up a system called HuggingGPT next to address this.
Yes, HuggingGPT is what the post categorizes as a controller model. It's a vital, practical contribution to the field because it forces us to rethink the role of the large language model. For a long time, we thought of the LLM as the monolithic worker that had to do everything itself.
It had to be the writer, the coder, the data analyst.
Right. HuggingGPT flips that. It treats the LLM as an orchestrator, or a brain.
Like a central nervous system.
Exactly. Imagine the LLM as a highly skilled project manager sitting at a desk. It receives a complex multimodal task from you. The first thing it does is task planning, breaking your massive request down into logical subtasks. Then it moves to model selection. It looks at a massive repository of specialized, narrow AI models.
Okay.
Maybe one model is a specialist at extracting text from images. Another is a specialist at generating audio. The controller LLM delegates the subtasks to these specialist models.
Oh, that's brilliant. It's the difference between hiring a brilliant generalist who stubbornly tries to do all the graphic design, the back-end coding, and the marketing copywriting themselves versus hiring an experienced executive manager.
Right.
The manager doesn't need to know how to use Photoshop. They just need to know how to hire the best graphic designer, give them a clear brief, and review their work. The manager just orchestrates.
That's exactly the paradigm HuggingGPT introduced. Once the specialist models finish their narrow tasks, the controller LLM takes all their outputs, synthesizes them in the task execution phase, and generates the final cohesive response for the user.
Wow. This architecture is absolutely essential as we move into enterprise environments where tasks become heavily multimodal or require deep domain-specific specialization that a single generalist model simply cannot handle efficiently. And speaking of specialized domain-specific environments, let's pivot to a really vital part of the digital workforce. The post shifts our focus from these general conceptual frameworks into the gritty reality of tasks that require strict reproducibility, specifically software engineering. This brings us to a really exciting part of the research. The SWE-Agent paper and the material around OpenHands. We are moving from API calls into the realm of code.
And this is where the theoretical rubber really meets the road. SWE-Agent is highlighted by the post as one of the most practical, paradigm-shifting papers mentioned in the entire chapter.
Why is this?
To understand its impact, we have to look at how we used to test coding models. Historically, we'd give an AI a short prompt, it would spit out a standalone function, and we'd check if it solved a narrow puzzle. But real software engineering isn't writing standalone functions in a vacuum. It's navigating complex, massive code bases with thousands of interconnected files.
It's finding a bug in a system you didn't build, buried in a folder structure you've never seen, right?
Precisely. What SWE-Agent did was treat the entire development environment as the core action space for the agent. It gave the AI access to a bash terminal,
Oh, wow.
allowing it to navigate directories, open files, write code, run shell commands, and crucially, execute test runs and observe the environment feedback. This is a massive leap up that representation ladder we talked about earlier.
Because it's operating in the most objective reality a computer has. The post lays down a very clear, hard rule here, doesn't it?
It does. The rule is if a task must be testable and reproducible, code is the required action surface. You don't want an agent just guessing how to fix a critical software bug in plain text and asking you to copy-paste it. You want it acting like a junior developer.
Right.
You want it writing the code, running a test suite, seeing the red error logs pop up on the terminal, reading those logs, and iterating its code based on that concrete, irrefutable feedback until the test passes green.
Because code is beautifully unambiguous. It either compiles and passes the unit tests, or it throws an exception. There's no vibes in compiling code. You can't bluff your way through a syntax error. And the post mentions that an initiative called OpenHands, which relates to the local OpenDev material in their research folder, takes this SWE-Agent concept even further, right?
Yes. While SWE-Agent proved the concept beautifully and set new benchmarks for resolving GitHub issues, OpenHands pushes this from being a narrow academic benchmark system into a general open-source developer agent platform.
So it's broader.
Right. It's about creating a holistic workspace. It's not just about fixing one bug. It's about providing a secure, interactive environment where the AI and a human developer can collaborate over long sessions, navigating files, and building software together. It's turning the agent from a one-shot script into an interactive collaborator.
Okay, here's where it gets really interesting for the listeners who might not be software engineers. Because as cool as autonomous coding agents are, the vast majority of enterprise work on this planet isn't writing Python scripts or fixing GitHub issues. It's dealing with business data. It's logistics routing, sales records, inventory databases, HR compliance logs.
Absolutely.
The post acknowledges this and pivots away from pure code to structured business data. It introduces two major pieces of research here: the Birdie paper and Spider 2.0.
This is a crucial pivot, and honestly, it's where the most immediate ROI lies for businesses adopting AI. The Bird paper centers database action as a real, immensely valuable enterprise surface. It acknowledges a fundamental truth. Many of the most important workflows in the global economy aren't about an agent browsing the public web or writing a new app. They are about structured data agents.
Right.
The ability to accurately query, transform, and reason over massive, complex SQL databases is the holy grail for enterprise intelligence.
Let's ground this. If I'm a chief revenue officer, a coding agent doesn't help me figure out why Q3 sales dropped in the Midwest. I need an agent that can speak to my relational database. But writing SQL queries is notoriously tricky for AI because every company's database is entirely custom, right?
Exactly, and that is what Spider 2.0 tackles. Historically, AI researchers evaluated text-to-SQL capabilities using very clean, narrow benchmark prompts. They'd give the AI a perfectly structured database with beautifully named columns like customer first name and ask it a simple question.
Yeah, totally unrealistic.
But Spider 2.0 pushes SQL agents away from those sanitized environments and forces them to deal with realistic enterprise workflow complexity.
Because real-world databases are absolute nightmares.
They are messy, organically grown beasts. They have weird, cryptic column names like custod99arab. They have missing data, convoluted schemas with dozens of overlapping tables, and legacy architecture from 20 years ago. What Spider 2.0 proves is that to have a reliable data agent, it must be able to explore the database structure interactively, understand the nuance of the enterprise's specific data dictionary, and write highly complex joins to extract the truth.
And if a business workflow is heavily data-centric, the post is very prescriptive about how you should build your agent.
The post states unequivocally that database or SQL action is the mandatory choice for the agent's surface. You don't export your database to a CSV and ask the language model to read a million rows of text in its context window. That is slow, expensive, and prone to massive hallucinations.
Right, that's just a bad idea.
Instead, you give the agent the tool to write and execute SQL queries natively, letting the database engine do the heavy lifting and returning only the specific answer.
That makes total sense. You use the tools designed for the job. You use APIs for interacting with cloud services. You use code for building software. And you use SQL for interrogating databases. It's a very clean, logical world. But let's step outside the laboratory.
Okay.
What happens when a clean API just doesn't exist? What if the data or the function you need is locked behind an old vendor website that doesn't offer a neat, structured way for a machine to talk to it? The post dives into the wild to address this, bringing up a series of web and mobile papers: Web Agent, Mind2Web, Mobile Agent, and App Agent.
Right. The real world isn't always accommodating. We don't live in a perfectly structured digital utopia. Sometimes the only way to get something done is through a user interface built for a human. When an API doesn't exist, but a website exposes a stable flow, browser action becomes a necessary path. The Web Agent paper is highlighted by the post because it demonstrates digital action over real, complex websites, not just simplified HTML toy interfaces built for research.
So what does a web agent actually do? Is it just clicking randomly?
Not at all. It reads the underlying code of the web page, the document object model, or DOM. It processes the HTML tags to understand where the text boxes, buttons, and dropdowns are. What WebAgent showed was that an agent can actually plan a sequence of actions over this structure.
Like a multi-step process?
Yes, it can maintain context over a long period, executing multi-step tasks like logging in, searching for a specific product, filling out complex shipping forms, and navigating multi-page checkout flows without losing its place.
And the post also mentions Mind2Web. How does that build on navigating websites? I assume it's about generalization.
Precisely. Mind2Web frames web action as a robust generalist capability. A true web agent shouldn't be a scripted one-off. In the old days of robotic process automation, developers would write a brittle script saying, go to coordinate X, Y, and click, then wait 2 seconds, then type. If the website moved the button 1 inch to the left, the whole script broke.
Oh man, I built those scripts. They are miserable to maintain.
Exactly. Mind2Web demands that an agent needs to understand the structure of the web itself. It has to understand how navigation flows typically operate across different domains. It has to dynamically read the web page and adapt to a site it has never seen before. Reasoning out that the shopping cart icon generally means the same thing, whether it's on a clothing retailer site or an electronics store. It's a massive step toward true digital autonomy.
But the wild gets even wilder, because not everything is on the open web with nicely readable HTML code. The post brings up Mobile Agent and AmbAgent. These deal with multimodal environments and mobile devices. Sometimes the action surface isn't typed at all. You can't see the code behind the app.
Yes, and this is where we reach a truly difficult frontier. Action surfaces aren't always neat code or structured web pages. Think about legacy enterprise software running on a virtual machine, or closed proprietary smartphone applications like a rideshare app or a mobile game. There's no API for the agent to call. There's no HTML code for it to read. In these cases, agents are forced to interact directly at the interface level, the graphical user interface, or GUI.
So the AI is essentially just looking at the screen.
Exactly. Mobile Agent and AmbAgent explore how agents can be designed to interact with smartphone screens entirely visually. The AI receives a screenshot of the device. It uses visual perception models to identify icons, text fields, and interactive elements. Then it outputs commands like swipe up, tap at these XY coordinates, or type hello. It is navigating the system exactly like a human user would, purely through visual input and simulated physical output.
Which sounds incredibly futuristic, right? I've seen these demos on social media, an AI just looking at a screen, playing a video game, or ordering an Uber. It looks like the ultimate manifestation of artificial intelligence. But the post introduces a paper called Omniparser that acts as a bit of a cold water reality check regarding this kind of visual interaction.
It is a massive reality check, and it's so important for our listeners to understand this. While those demos look magical, Omniparser is what the post calls a bottleneck paper. This raises an important question. If visual AI looks so human-like, why do the authors of this post consider GUI action to be the absolute fallback of last resort?
Yeah, if it can see the screen like I can, why is it a bad idea?
The answer Omniparser highlights is the inherent visual bottleneck. When a human looks at a software interface, our brains instantly process immense amounts of context, hierarchy, and design language. We know that a grayed out button means unavailable. We know a magnifying glass means search. When an AI tries to use a computer visually, it often fails horribly. Not because it lacks reasoning, but because visual interfaces are inherently ambiguous to machines.
Can you break that ambiguity down? What does the AI actually see?
To an AI, a screenshot is just a giant matrix of millions of colored pixels. To make that actionable, it requires a highly complex conversion process. A parser model has to scan those pixels, draw bounding boxes around things it thinks might be buttons, attempt to read the text inside them using optical character recognition, and guess the spatial layout. It has to translate a 2D image back into a structured, machine-usable format. This translation layer is incredibly fragile.
I see. If two buttons are close together, the AI might combine them into one bounding box. Or if the background color changes slightly, it might lose the text. It's relying on a very shaky foundation to make its decisions.
Exactly. And because it's so fragile, the actions are slow, expensive, and highly prone to error. Which brings us perfectly to the core operational framework of the entire chapter, what the post calls the method comparison matrix.
Yes. This is where the post crystallizes all these different abstract research approaches into a clear set of rules of engagement for building real systems. It's basically an if X, choose Y decision framework. Let's walk through this matrix, because if you are a listener trying to build an automated agent for your company, or if you're investing in AI startups, This matrix feels like the ultimate cheat sheet for separating good architecture from doomed architecture.
It really is the architect's blueprint. The matrix meticulously breaks down the 5 different action surfaces we've just discussed, evaluating them on their best use, their main strengths, their critical risks, and crucially, when you should escalate to a more difficult surface. Let's start at the very top of the hierarchy with the most reliable preferred method, typed API tools.
Okay, typed APIs, when should we use them?
The best use for APIs is interacting with modern business systems, cloud services, and anything that has a defined back-end interface. The main strength is that API calls are perfectly replayable and inspectable. You know exactly what JSON data went in and exactly what data came out. It's highly measurable.
But there is a risk, right? Even with APIs, what's the main risk here?
The main risk is weak schemas. If the API documentation is poorly written, or if it requires bizarre, non-standard arguments, the agent will struggle to format the data correctly and will hallucinate inputs. But according to the matrix, you should only escalate away from APIs when the required system simply has no usable API available or it's locked behind a paywall you can't access. You always try to use an API first.
Okay, the second surface in the matrix is code execution. Best use. Complex software engineering, math, and data transformation tasks.
Yeah.
Main strength. It's intrinsically executable, testable, and replayable.
Exactly. You use code when logic and math are required because LLMs are bad at math but great at writing Python scripts that do math perfectly. But the main risk here is severe and we need to pause on it. Unsafe scope if poorly sandboxed.
Let's define sandboxing for the audience. What happens if we don't do it?
A sandbox is an isolated testing environment. If you give an agent the ability to execute code, and you just let it run on your main laptop or your production server without restricting its permissions, the results can be catastrophic.
Yikes.
Imagine an agent trying to clean up some temporary files, and because its logic is slightly off, it accidentally executes a command that deletes your entire operating system directory. Or it gets stuck in an infinite loop and consumes massive cloud computing resources, racking up a $10,000 bill overnight. You must constrain the environment.
High power, high risk. And when do we escalate away from code execution?
You escalate away when the target system is external and completely UI bound, meaning code can't reach it because there are no programmatic backdoors.
Okay, the third surface is database or SQL action. Best use. Enterprise analytics and structured data work. Main strength. Incredibly strong structure and mathematically measurable outputs.
The risk with SQL action is schema drift. This happens when the human engineering team changes the structure of the database. Maybe they rename a column from revenue to gross revenue, but the agent isn't updated. The agent's queries will suddenly fail. There's also the risk of unsafe queries, like an agent accidentally dropping an entire table or writing an inefficient join that pulls millions of rows and crashes the database server. You escalate away from database action when the tasks depend on web or GUI state instead of pure data.
Which brings us down to the fourth surface, browser action, a best use. Web-native workflows like booking solutions or e-commerce, main strength. It works where clean APIs are incomplete or entirely missing.
But the risk increases significantly here. We are moving down the ladder of reliability. The main risk with browser action is brittle selectors and page changes.
Can you explain what a brittle selector is in this context?
Sure. When an agent reads a web page, it looks at the underlying HTML code. It might find the checkout button by looking for a specific name tag in the code known as a CSS class. Let's say it's called button checkout blue. The agent relies on that name tag to know where to click, but if the human web developer redesigns the site the next day and changes that name tag to primary action BTN, the visual button looks exactly the same to a human user. But to the AI reading the code, the button has vanished. The selector was brittle. It broke.
So web agents require constant monitoring because the web is constantly changing. And according to the matrix, you only escalate to the final surface when that underlying DOM acts as the HTML code of the web page, is blocked by security, or the system is highly visual, like a video game.
Which brings us to the bottom of the barrel, the absolute last resort in the architect's matrix. GUI action. Interacting purely with the visual interface using screenshots and pixel coordinates. The best use case is for closed, legacy interfaces, remote desktops, or mobile apps where you have zero backend access. The main strength is that it reaches otherwise completely inaccessible systems.
But the risk is immense.
Immense. GUI action has the absolute highest fragility and the weakest observability. It breaks easily. If a pop-up ad appears or the screen resolution changes, the AI clicks the wrong pixels. And worse, when it breaks, it's very hard for the system to understand why it broke through just looking at pixels. It doesn't get a clean error code. It just sees that the screen didn't change the way it expected. The rule of the matrix is clear. You escalate to GUI action only when every single cleaner, more structured surface we just discussed is completely unavailable.
That matrix is incredibly clarifying. It cuts right through the hype of AI that can use your computer. But the post also drops a really nuanced, interesting piece of advice about the tools themselves, regardless of the surface. It talks about tool design, specifically when to specialize tools versus when to keep them generic.
Yes, this is a very common debate among engineers building these systems. It's tempting to build one massive generic tool. For example, a single search database tool that the agent can use to search the HR system, the sales system, and the inventory system. It's attractive because it's less code to write initially.
But the post warns against that.
Right.
It advises specializing tools when domains differ enough that the failure handling or the schemas are distinct.
Exactly. The post argues that generic tool layers eventually fail at argument accuracy. If you have a generic search database tool, the agent has to figure out incredibly complex syntax to know exactly how to format the query for the HR database versus the sales database. And if the query fails, the generic error message won't help it recover. But if you specialize the tools having a distinct search HR database tool and a separate search sales database tool, you give the agent a much tighter, more predictable schema to work with. The instructions for each tool can be highly specific. This drastically reduces hallucinations and increases reliability.
It narrows the lane the agent have to drive in. Okay, so we've mapped out the surfaces, we understand the representation ladder, and we know how to design the tools. But how do we actually run this safely in production? Let's transition into what we can conceptualize as the engine room.
The engine room, I like that.
The post outlines the internal mechanics required to make these actions work without burning down your infrastructure. Reading this section really puts you in that rigorous researcher mindset. It breaks the engine room down into three crucial, distinct layers: execution, observation, and recovery. Let's dive deep into the first one, the execution layer.
The execution layer is where the theoretical intent of the AI becomes physical reality on a server. The post emphasizes the absolute, non-negotiable necessity of running actions in what we call a sandboxed, least privilege environment.
Least privilege, meaning you give the agent the absolute minimum permissions required to do its specific job and nothing more.
Precisely. You never, ever let an agent execute code or API calls with administrative root privileges on your main system. If it only needs to read a database, you give it read-only access. It cannot write, it cannot delete. The execution layer must also be responsible for two critical phases: pre-validation and post-normalization.
Let's break those down. What is pre-validation?
Pre-validation happens before the tool actually runs. The execution layer intercepts the AI's request and checks it against hard-coded rules. If the AI is trying to book a flight and it hallucinates a date in the year 2099, the pre-validation layer catches that obvious error and blocks the execution, sending an error back to the AI before it wastes an expensive API call to the airline.
That's a great safeguard. And post-normalization.
That happens after the tool runs successfully. APIs often return chaotic, messy data formats. Post-normalization cleans that data up, strips out the junk, and formats it uniformly before passing it back, which leads directly into the second layer, the observation layer.
Yes, the observation layer. The post is something really specific and vital here. The system must convert tool results into typed observations rather than just dumping raw text back into the model. Why is that so critical? Let's use an analogy here to make it clear.
Okay, imagine handing a human manager a 10,000-page, unformatted spreadsheet printout with 0 headers, 0 summaries, and tiny font, and expecting them to make a split-second, accurate business decision based on it. They would be overwhelmed. They would lose the plot entirely.
You'd probably just guess.
Exactly. The same thing happens to an AI. If an API returns a massive, unformatted JSON blob with 5,000 lines of metadata, or a code execution throws a giant, rambling stack trace of errors and you just dump all that raw text straight back into the LLM's context window, you will overwhelm its reasoning capabilities. It suffers from context pollution. It gets distracted by the noise.
So what does a typed observation do differently?
Converting results into typed observations means the observation layer acts as a filter. It extracts only the relevant actionable fields and presents them in a clean, consistent, machine-readable contract. Instead of 5,000 lines of JSON, the observation layer hands the AI a neat summary. Status success, error code null, return drows 15. A clean observation contract stabilizes the entire reasoning loop, keeping the model focused purely on the outcome of its action, not the noisy formatting of the back-end system.
I love that. It's about protecting the AI's attention span. But in the real world, things will go wrong. The API will time out, the database will be locked, the credentials will expire. Which is why the third layer, the recovery layer, is so fascinating to me.
The recovery layer is what separates a brittle script from an autonomous, resilient agent. The post insists on explicit engineering for tracking retries, failures, and fallbacks.
And the post makes a really sharp point about how errors should be handled. It says tool errors must create machine-readable state.
Yes, this is a common trap developers fall into. If an agent tries to query a database and the table doesn't exist, the observation shouldn't just be the AI generating a free-form conversational apology, like, "I'm so sorry, but it appears I couldn't find the data you requested. Would you like me to try something else?"
Right, because that apology is useless for a system trying to automatically recover. The system doesn't know why it failed.
Exactly. The error needs to be captured as a structured, quantifiable state. The recovery layer should generate an observation like, error type schema mismatch. Details, table users 2024 not found. Current retrant count 1. Max retries 3. This structured state allows the agent's logic to methodically try a different approach, perhaps calling a different tool to look up the correct table name, rather than just endlessly repeating the exact same broken query in an infinite loop and apologizing for it every time.
So we have this incredible architecture. We have the execution sandbox, the observation filters, the structured recovery layers. So what does this all mean for how we actually judge these systems? We are spending millions of dollars and countless engineering hours building these architectures. The post spends a significant amount of time on evaluation and anti-patterns. How do we measure success correctly in a world of autonomous agents?
We measure it by completely abandoning what the post brilliantly calls in-task vibes.
In-task vibes. That might be my favorite phrase in the entire piece. It perfectly captures how the general public, and even many tech executives, evaluate AI right now. It's when you ask an AI to do a complex task, it spits out a nice-looking, formatted final answer, and you just glance at it and go, well, the vibes are good, it looks confident, it must have worked, without actually verifying the mathematical or logical steps it took to get there.
It's a dangerous trap. The post firmly states its thesis on evaluation. The right metric for an agent is not, did the final answer look good? The right metric is, did the system execute the correct sequence of steps safely, logically, and reproducibly? To measure that, you have to look under the hood. The post provides a list of highly practical, hard engineering metrics that every team should be tracking.
Let's run through those metrics because they are the new KPIs of the AI era.
First, you need to measure tool selection accuracy. Out of 100 tasks, how many times did the AI pick the exact correct tool from the catalog? Second is argument accuracy. Even if it picked the right tool, how often did it format the JSON parameters flawlessly on the first try? Third is the overall action success rate. Did the tool actually run and return the expected data without throwing an external error?
And it also mentions measuring the recovery rate after failure, which ties directly back to that structured error state we just discussed. If a tool call fails, what percentage of the time does the agent successfully pivot, correct its mistake, and complete the task versus just giving up or hallucinating?
Exactly. You also need to track retry count. Is it taking 10 attempts to get a query right, which drives up API costs? You have to measure latency and cost per action. If an agent takes 5 minutes and $2 worth of compute to execute a task a human could do in 30 seconds, it's not viable. And finally, the ultimate metric, replayability and auditability. If you look at the system logs and you can't replay exactly what the agent did, step by step to arrive at its conclusion, you don't have a reliable enterprise system. You just have an expensive black box.
And with all those rigorous metrics in mind, the post actually does something incredibly generous. It doesn't just leave you with theory. It provides a recommended step-by-step build order for anyone designing an agentic system from scratch. It tells you exactly where to start your engineering efforts.
It's a fantastic roadmap designed specifically to keep developers on the safest, most stable rungs of the representation ladder for as long as possible.
Let's walk the listener through this build order. Step 1. Start with type tool calls over APIs. Before you do anything else, get your clean, structured integrations working perfectly. Prove your model can construct arguments.
Step 2. Add code execution, specifically for tasks that require complex math, data transformation, or reproducibility, but ensure it is strictly sandboxed.
Step 3. Only after APIs and code are mastered do you add browser or SQL action. and only for workflows where the environment specifically demands navigating a web structure or a raw database.
Step 4. Add GUI automation strictly as an absolute last resort, reserved only for constrained legacy systems where no other access point exists.
And step 5, which I think is a great piece of advice for product managers, expand your tool catalogs only after you have thoroughly measured and understood your tool use failure modes on a small set of tools. Don't just dump a massive catalog of 100 tools on an agent on day one and hope for the best.
Master the small catalog first. Measure the argument, accuracy, and recovery rates. Once those are high, then you scale. And to reinforce that disciplined approach, the post explicitly warns against several dangerous anti-patterns. These are the seductive traps that builders fall into when they prioritize marketing hype over robust architecture.
Let's run through those anti-patterns to avoid. They feel like the 10 commandments of agent design. If you are building AI, listen closely to these.
The first anti-pattern is, do not start with general computer use as the default action surface. Do not build an agent that immediately tries to take control of the user's mouse and keyboard to solve a problem if a clean back-end API exists to do the same thing. It is unnecessarily brittle, slow, and prone to visual errors.
The second anti-pattern. Do not let one single agent hold every tool and every permission. That is a massive security and reliability nightmare. Just like you don't give a first-day intern the master administrative keys to the entire corporate infrastructure, you shouldn't give a single monolithic agent access to every database, email server, and financial API simultaneously. Break them into specialized roles, like the controller model we discussed earlier.
Third, do not treat raw tool output as final truth. Always have that observation layer we discussed. You must normalize, filter, and mathematically verify the results of an API call or a code execution before you allow the agent's reasoning layer to act on it.
And the final anti-pattern. Do not ship action layers into production without comprehensive logs and replayability infrastructure. If your agent breaks a business process and you have no logs of the exact tool schemas it tried to execute or the sequence of steps it took, you are flying entirely blind. You have no way to debug the system.
Those anti-patterns really summarize the entire ethos of Chapter 8. They demand engineering rigor, precise measurement, and structural discipline over flashy, unpredictable demonstrations.
They really do. This has been such a dense, rewarding deep dive. We've covered an immense amount of ground today, from the foundational theories of ToolFormer to the architectural blueprints of the engine room. The bottom line we are taking away from the post today is clear. For AI to truly evolve, action must be structured, bounded, and measurable. The true transition from being just a helpful conversational assistant to a genuine, reliable agent happens only when a system can take replayable, inspectable actions in software. It is not about when the AI sounds more autonomous. It is about when it can mathematically prove its autonomy through structured, safe execution.
And if we look at the trajectory we've traced today, from the earliest models guessing at text, up the representation ladder to rigid code and type tools, it leaves us with a really provocative, perhaps slightly unsettling thought to mull over.
I love a good provocative thought. Lay it on me.
If the entire evolution of reliable AI agents relies on climbing that representation ladder, if the goal is moving away from the ambiguous plain text and the brittle, unpredictable graphical interfaces that humans prefer, and moving toward the clean APIs, rigid code, and testable environments that machines require, then the biggest bottleneck to the future of artificial intelligence isn't actually the intelligence or the reasoning capabilities of the underlying models themselves. We might already have models smart enough to do the work.
Oh, wow. If the intelligence isn't the bottleneck, what is it then?
The bottleneck is the messy, unstructured, organically grown digital world we humans have built for ourselves over the last 40 years. We built millions of websites and software interfaces designed specifically for human eyes. We built them with visual ambiguity, shifting layouts, clever CSS tricks, and unstructured data. Humans thrive in that visual ambiguity. Machines drown in it.
They need structure. They need APIs and schemas.
Exactly. So the provocative question is this: will the rise of AI agents force us to entirely redesign our software ecosystem? Are we going to reach a point where we have to essentially rebuild the internet and our enterprise systems from the ground up, creating a parallel digital architecture with interfaces meant not for human eyes, but specifically optimized for machine actions? Are we building a new internet just for the agents?
That is an incredible point to end on. If the agents can't reliably navigate our messy, human-centric world, maybe we have to build a cleaner, parallel reality for them to operate in. A machine-readable layer over the human world. Wow. we're going to have to leave it there for today, but what a fascinating, massive place to stop and think. Thank you so much to everyone listening for joining us in the researcher's seat today. We hope you found this exploration as insightful and as grounding as we did, and we strongly encourage you to keep exploring the layers of AI evolution on your own. There's always more depth to uncover. Until next time, keep thinking out loud.